Hi, everyone. I'm Landon Ivy. I'm a fourth-year PhD student from Cornell University, part of Professor Wong's Sonic News Lab. Yeah, so basically, I'm just going to go over my outline here, which is so there's the motivation, which would be that in certain environments, like for instance, if you run a Navy vessel or in a military operation where you basically you use a precision sensor, you might want to have a way to reproduce that sensor or have a temporary replacement for it using 3D printing. That's what the Army Research Laboratory is interested in for this. And then I'll talk about an example sensor, in this case, a strain gauge based pressure sensor. And then I'll cover my experimental results where I measure the resistance change versus input pressure. And finally, I'll summarize. So, this is a rendering of the fully assembled pressure sensor. What we're making is a diaphragm, like a circular diaphragm vented gauge pressure sensor. So as you see, there's an airtight chamber underneath this Kapton diaphragm, and there's an inlet port, a lever lock, and then on the outlet, there's just like an NPT port, and so we just put a push to connect pneumatic port on that. So the two reasons why this is an interesting project is because, as far as I know, it's the first demonstration of a diaphragm pressure sensor of this type that is meant to work with pneumatics. It could also work with water or whatever that's produced using laser-induced graphene for the resistive element, and then it's wired up and sealed with printed electronics techniques. So the way that we were able to produce the encapsulation and the wiring layers was with this commercially available BotFactory PCB printer, which is a thermal inkjet printer. It's able to produce pretty good PCBs in a pretty short amount of time on site, like you would with an FDM printer. Here's some of its capabilities. In this case, we're only using this first capability, which is the fact that it can print dielectric ink and conductive ink layers, but it can also deposit solder paste for placing surface mount components. And then it can also, if you give it a pick and place file, it can actually place all of your ICs for you, and it can also apply thermal refill profiles. So these last two abilities we kind of take advantage of in the future. Basically, these piezo-resistive based pressure sensors, they give readouts even whenever you configure them, like as a Wheatstone bridge, you get readouts that need amplification usually in order to actually have a usable voltage difference. So it would be cool to have the amplifiers and all of that circuitry just on the same sheet of Kapton as the pressure sensor. So before we could actually start using the BotFactory to do anything cool with the pressure sensor, we needed to actually characterize it, because BotFactory is a fairly new company in New York. We've only sold like a couple hundred units. And so it was kind of up to us to actually figure out what print settings to use. So a couple of the print settings that are really important on this characterization board. On the x-axis is the offset from the default height that you're printing from the substrate, which is 1.5 millimeters. So like this 0.0 millimeter offset is actually 1.5. So you see that as you go further away from the substrate, obviously you get worse results. The closer you can get, the better. So if we actually were to go negative, like all the way down to like maybe 0.5 millimeters away from the substrate, we would get even better results, but this is sufficient. Another thing that's important is the number of passes. So if you need a more conductive sheet metal here, then you can increase the number of passes. But as you see here, I guess I don't have a zoomed in image, but this is worse than this because the more passes you have, the more filled out the dimensions get. Here's a zoomed in image of the best result that we got, and you can see that we were able to produce reliably minimum trace width of 100 micrometers with the printer and a minimum trace gap of 200 micron. So here's the question: why even use laser-induced graphene piezoresistors whenever you could just print your resistive network? And there are plenty of resistive inks that we could have used with the BotFactory. BotFactory themselves sells one, but they don't anymore, and that's because it constantly clogged with their HB thermal inkjet nozzles. So the other reason, other than just difficulty with working with those inks, is that most like metal foil based pressure sensors and strain gauge sensors, they have very, very fine, typically photolithography defined features. And as you see from before, this printer is only capable of producing so 100 micron features. So the resolution issue. So that hopefully explains why using laser-induced graphene, like if you can just write directly into your Kapton diaphragm, your whatever piezoresistive pattern you want, then you're only limited by the spot size of your laser cutter. So the laser cutter that we were using is a pretty cheap, commercially available printer. It's called the VersaLaser 3.6, and it has two different optical sets. It's modular. So we were using the smaller attachment, and it gives you a spot size of 25.4 micron. And then another thing I'd like to touch on, which is kind of important, is there's two different laser modes with this laser cutter. This is pretty common with laser cutting. Raster mode and vector mode. So with raster mode, we provide like an SVG, which has like built-in spaces, kind of like you would use for mask writing. And in that case, it basically just decides how it wants to actually move the laser in space. Here, it's doing like a square grid cutoff of your building shapes. But what we wanted to do is actually write in vector mode. And in that case, it just literally follows the lines that you supply it. So you are giving it steps. And we wanted to do this so that we had complete control over how our actual patterns were being formed, so we would get repeatable results. So now we need to characterize the laser cutter, and we did that by doing a similar characterization sheet where we're varying one print parameter on the x-axis and another on the y-axis. The two important characteristics here, or the two important characteristics here, are laser power and laser travel velocity. These are both software settable with the VersaLaser. So they're highly repeatable as long as you're focusing to the substrate every time, you can get the same results. So we have like a 125 micron shear Kapton here. And as you see, if you go way too fast, even with, and you have low power, you don't get any graphene at all. In the far right, bottom right corner, you have an almost black, like burnt out piezoresistive rectangle. And so basically like the Goldilocks zone is like somewhere here. Yes. Okay, I'll get to it. We also did this on FR4 because we hadn't seen anyone do that. Here's the way we narrow the results, just pick them visually. And then we further narrowed them with the Raman spectroscopy. Basically, we compared them against the monolayer graphene, which is shown in blue, and the microscope images for each. And then from that, we were able to identify the best combination. Here's the resistor pattern. We have 4 resistors here. And then here's the process flow. So we basically print all of these fiducial windows on the first step with the BotFactory. And then we use the laser cutter to print our resistor network. And then we go back to the BotFactory to print our 6 wires. And then shown in blue is the dielectric key, also printed with the BotFactory. This serves to seal up the graphene so that it doesn't flake off and change resistance over time. So here is like the actual assembly for the pressure sensor. I used Object 30 3D printer, which is a PolyJet printer that has water soluble support material. And so this is just all the different parts. We also laser cut the gasket to make an airtight seal. And here's all the resistances labeled. That'll be important in the next slide. And here's like the dimensions for the chamber and the diaphragm diameter. Here's the experimental setup that we have. So what I'm doing is I'm just using a syringe pump where I can change I can set exactly the volume reduction that I want. And then I'm using a digital pressure sensor to create these plots on the next slide. So here I'm showing the syringe volume that I set with the syringe pump. And then on the y-axis, you see the resultant pressure change. And then also the normalized resistance change. And from that, I can calculate the sensitivity, which was 5 kilopascals. And that's similar to the only other LIG strain gauge I could find. Yeah, so in summary, basically we've shown a hybrid approach to making piezoresistor based sensors. This is PE and LIG, and we plan on using this or a continuation of it to make gas sensors, force sensors, and other more complicated sensors. And here's what I plan to do in the future. Basically want to use FEA optimization to improve the results of all the physical properties. And we also are setting up an automated workbench to test these, to stress test them for longevity. Here's all the people that worked on this project. And any questions?